Continue our discussion on superposition of waves, and what we have here are two waves which are heading towards each other, and they are same in frequency and same in amplitude. The only difference is that they are moving towards each other. And what happens is that this red shows the superposition or resultant of these two waves. So we see red actually goes to a maximum value, which is the resultant of the two waves, and also it becomes zero, a straight line. And the moment the red wave is on top of the blue one, red assumes the maximum shape or the maximum value, and the moment the black is sort of opposite to the blue one, then red goes to zero. So this is what is happening here. We have two waves, something like this, and when they are on top of each other, then they produce a bigger wave. Of the same frequency. And when they are against each other, something like this. Not exactly, I haven't drawn it very properly, but something like this. Then you get zero. And you can have situations when there is something in between. Something in between. In this case, we get something in between. So the wave goes from medium to zero to in between to a maximum. So this is what is happening. But for this particular case, we saw that they were heading towards each other on a straight line. What about the case when the two waves sort of travel like this? What happens then? And to start talking about that, we need to discuss few things. First of all, this we can only talk about this the resultant of two waves or superposition of two waves when some wave has traveled for distance x1, the other wave has traveled for different distance x2, when the two waves are coherent in nature. What does that mean? We can only talk about maxima or minima or anything in between when the two waves are coherent. What does coherent mean? Coherent means they follow the same equation, which means if this wave is expressed as a sine omega t plus 5, this equation is also expressed as the equation followed by this wave is also expressed as a sine omega t plus 5. Which actually in practical terms means they are being produced by the same source, which means, let's say, if you have an electric bulb and this is producing light, and you put sort of a perforated membrane in between, then light emitted from these holes here is going to be coherent. And then you can talk about how these two waves superimpose somewhere outside, somewhere here in this region. So these two are the two sources which are coherent in nature. So this guy is also going to produce and follow equation a sine omega t plus phi, and this guy here also is going to follow the equation a sine omega t plus phi. These are coherent in nature. The only difference between these two waves is that this guy has traveled a lesser distance, so it has taken a lesser time, and this guy has traveled a longer distance and has taken a longer time. So let's say if this has traveled distance x1 and this has traveled distance x2, x2 minus x1 is called the path difference between the two. It's called the path difference between the two waves. Just to give you an sort of a side information, if we remember properly, if there was a wave heading towards, let's say, some rigid end, and the wave got reflected backward, then we remember that whenever there is reflection, the wave suffers a phase difference of pi over 2, if you remember properly. the wave goes from sine omega t plus phi to it goes to sine omega t plus phi plus pi over 2. So this is the outgoing wave, and this is the incoming wave, and this is the outgoing wave. So it suffers a phase difference of pi over 2 when it gets reflected. Well, this you can also say that it suffers a path difference of lambda over 4. The same, the two definitions are the same, and it will make more sense. So on reflection, a wave suffers a phase difference of pi over 2 and a path difference of lambda over 4. They tell the same information, but let's see what's happening here so that we can understand what we actually said here. So the path difference is defined as x2 minus x1. Okay, well, let's say, so what is that thing that is changing the amplitude of the wave? It's this number inside the brackets that is changing with time, and because this is changing with time, the amplitude also changing with time, because sine of that number gives you different values at different times. So it's this angle omega t plus phi that is changing with time. So omega t plus phi is has some value here, and sine of omega t plus phi has some value here. As we move forward, that omega t plus phi changes, and sine omega t plus phi also changes, and that's why you have different amplitude here. So both the waves start with the same number here, omega t plus phi, but this guy here has a different angle or different number when it goes from here to here, and this guy here has a different omega t plus phi when it goes from here to here, which means, let's say the first one took time t1 and the other one took time t2, which means the angle, let's say you started with an angle of, I don't know, let's say phi naught, phi 0 and phi 0. So phi 0 is the angle when you started tracking the waves. So the number inside the bracket is phi 0. That's the starting position. So the number should change as omega naught plus, as the time changes, it should change as omega t. So here, for the first wave, it's phi naught plus omega t1. Similarly, for the second wave, it's phi naught plus omega t2. So this guy ends up with a different phase, total phase, the end phase, and this guy ends up with a different end phase. And the phase difference is nothing but the subtraction between these two. And this is called the phase difference. Right? You might be wondering, what is phi naught? Phi naught is some initial value of the omega t plus phi, which means some value of t here with which you started, and let's say you started with t equals t naught. So phi naught is nothing but omega t naught plus phi, that is phi naught. So this is phi naught for both the waves. But as phi keeps changing because of omega t, this is how it changes. Okay, this is phase difference, and you can actually relate these two very simply, because you know that velocity of the wave is given as lambda over t. That is the velocity of the wave. So you will actually find that the phase difference, let's just call this PD, phase difference, is nothing but 2 pi multiplied by x2 path diff. Well, actually I should write ph to say phase and pa to say path difference. Doesn't really look nice variable, so let's call this I don't know, what should I call them? Let's call this delta x, and let's call this delta phi, right? So let's remove all this nonsense here. So we can say delta x, you can very easily prove that delta x or delta phi actually is nothing but 2 pi delta x divided by lambda, where lambda is the wavelength. You can very easily verify that using simple formulas like this. and like omega equals 2 pi f, or f equals 1 over t. Using all these formulas, you can verify this formula. So this is the path difference between the two waves, and this is the phase difference between the two waves. So the waves should be on top of each other if you want a maxima there. So when these two waves are going to be on top of each other, well, you see these two waves differ from each other in multiple of lambdas, which means if the path difference between these two waves is 0, then you have maxima. If the path difference between these two waves is lambda, which means this wave, and you move it further down by a lambda, then what you achieve is something like this, which means the second lambda. So you again have a maxima if the path difference between these two waves is a multiple of lambda. So it can be either 0, which means just on top of each other, or it can be lambda, which means on top of each other, but this guy, the second guy, has shifted forward by lambda, or it can be 2 lambda, which means you shift this wave 2 times more, 2 lambda more, because it repeats itself. Every time you shift it by lambda, you see you have a matching condition. The two waves match properly. So whenever path difference is multiple, or let's do a new one, whenever delta x is multiple of lambda, it's the maximas here. The two waves have the same value, which means, let's say this guy was traveling like this, and this guy was traveling like this, or let's see in just one. So this guy traveled from here to here, and it achieved somewhere here. It reached somewhere here. And similarly, this guy started traveling from here and reached somewhere here. So these two, when they combine in a way something, I don't know, something like here, then the two maximas match up and they produce a maxima here. So the condition is this wave has a maxima, or the maximum amplitude, and similarly this wave also has a maximum amplitude, and the two maximum amplitudes match up to produce a superposition or constructive interference, and that happens when x1 minus x2 is multiple of lambda, right? So the two waves will have, both the waves will have a maximum when this is satisfied, and whenever both the waves will have maximum, they will simply add up to produce a bigger maximum. But if x1 minus x2 is multiple of n lambda over 2, where n is odd, which means the path difference between them is a multiple of lambda over 2, but an odd multiple of lambda over 2, which means lambda over 2, 3 lambda over 2, 5 lambda over 2. Then we see when these two waves travel, and when they reach here, what we'll find that the first wave will look like this and the other wave will look like that. So they'll cancel each other after traveling like this. So whenever the path difference is like this, then we have a minima there. So the basic idea is the path difference should be a multiple of lambda, and when that is true, when this wave reaches here, it looks like this, and when the other wave reaches there, it also looks like this, because because of the way it has traveled, and then you get a maximum. So we'll solve some problems and we'll understand more in more details.